Welcome, cosmic explorers. Get ready for an extraordinary journey to the frontiers of modern astronomy. In this video, we'll voyage beyond our solar system to uncover the thrilling hunt for exoplanets, distant worlds orbiting alien suns. This isn't just science fiction, it's a real scientific revolution reshaping our understanding of the universe, revealing planets of fire and ice, uncovering systems stranger than imagination, and bringing us closer to answering humanity's oldest question: are we alone? Just 3 decades ago, we knew only the planets in our own solar system. That changed dramatically in 1992 with the first confirmed detection of an exoplanet orbiting a pulsar, a celestial lighthouse born from a dead star. Then in 1995 came the groundbreaking discovery of 51 Pegasi b, a hot Jupiter orbiting a sun-like star. These breakthroughs ignited an explosion in exoplanet science. Today, as of June 2025, we've confirmed a staggering 5,926 exoplanets in 4,419 unique planetary systems, with nearly 1,000 systems hosting multiple planets, a monumental leap from fewer than 50 known exoplanets at the start of the millennium. How did we find these distant worlds? Most hide in plain sight through subtle starlight clues. The transit method, detecting the telltale dip in a star's brightness as a planet crosses its face, accounts for about 75% of discoveries, powering missions like NASA's Kepler and TESS. The radial velocity method, measuring a star's rhythmic wobble caused by an orbiting planet's gravity, reveals another 19%. Together, these techniques paint a picture of a galaxy teeming with planets. Remarkable statistics suggest 1 in 5 sun-like stars may host an Earth-sized world in its habitable zone, the region where liquid water could exist. Factor in the countless red dwarf stars, and our Milky Way alone could harbor billions of potentially habitable terrestrial planets. Recent discoveries are rewriting textbooks. NASA's TESS mission spotted TOE 700e, a rocky world 95% Earth-size, snugly orbiting within its small star's habitable zone every 28 days. The James Webb Space Telescope, JWST, is probing the TRAPPIST-1 system, where 7 Earth-sized planets circle a dim red star 40 light-years away, with 3 in the Goldilocks zone. JWST also achieved a milestone in 2025 by directly imaging Saturn mass TWA-7b, the lightest planet ever captured this way. Other wonders abound. Rocky planet BD plus 054868 sports a 5.5 million-mile-long comet-like tail as its atmosphere is blasted by stellar radiation, while JWST's images of gas giants YSES-1b and YSES-1c reveal bizarre features like dark silicate clouds and a glowing dust disk that could be forming moons. This explosion of discovery is more than a cosmic census. We're now entering an era of deep characterization. With instruments like JWST analyzing atmospheric chemistry through starlight filtering past planets or blocking out starlight to glimpse the worlds directly, we're hunting for biosignatures, potential fingerprints of life. Every new world challenges our assumptions, revealing planetary systems wilder than anything near our sun. Join us as we explore how these alien worlds form, how common habitable environments might be, and whether we might detect signs of life beyond Earth, transforming our place in the cosmos from a solitary outpost into a single data point in a vast, interconnected universe of possibilities. So we stand at the threshold of a new era, one where merely detecting exoplanets isn't enough. Now we're dissecting the very air of these alien worlds, peeling back layers of gas and chemistry to understand their stories. This deep characterization transforms pixels of light into narratives of formation, evolution, and perhaps even habitability. The key? Starlight itself. When a planet transits its star, a tiny fraction of that light filters through its atmosphere. Molecules within the atmosphere absorb specific wavelengths, leaving unique chemical fingerprints in the spectrum. This is transmission spectroscopy, our cosmic chemical analyzer. Alternatively, when we directly image planets, we split their faint glow into rainbows, reading atmospheric secrets from their infrared whispers. Consider the James Webb Space Telescope's revolutionary work. It confirmed water vapor shrouding the scorching gas giant WASP-96b, 1,150 light-years away, but with a twist: high-altitude clouds that defied expectations. Even more groundbreaking was its detection of carbon dioxide in WASP-39b's atmosphere, 700 light-years distant. Why does this matter? CO2 acts as a cosmic thermostat. Its presence helps us model atmospheric stability and climate. But Webb went further, spotting sulfur dioxide around the same world, evidence of active photochemistry, where starlight triggers complex reactions akin to Earth's ozone formation. Suddenly, we're not just seeing atmospheres, we're watching alien weather systems and chemical factories in action. Now let's confront strange realities. Red dwarfs, small, cool stars that outnumber Sun-like stars, host the majority of known habitable zone planets. But could life thrive there? Proxima Centauri b, just 4.2 light-years away, orbits so close to its star that it's likely tidally locked. One side perpetual day, one eternal night. Atmospheric simulations suggest potential eyeball configurations. A dayside ocean boiling under relentless radiation, bordered by ice continents with a hurricane-strength jet stream transporting heat. Then there's the hellish 55 Cancri e, a super-Earth blanketed in oceans of lava. Webb's thermal maps revealed a molten surface reaching 1,500 degrees Celsius, with vaporized rock potentially raining gems. Meanwhile, Kepler 70b endures even greater extremes. A stripped core orbiting its white dwarf star every 5 hours, temperatures hotter than our Sun. These extreme laboratories force us to rewrite planetary formation theories, proving that solar system rules are mere suggestions. Of course, the ultimate quest is for life. Biosignatures, combinations of gases unlikely without biology, are the holy grail. Oxygen and methane coexisting, for example, hint at continuous replenishment since they normally destroy each other. But caution is critical. Venus taught us that. Its CO2-rich atmosphere once sparked speculation about life, yet it's a sterile greenhouse. Similarly, abiotic processes on volcanic worlds can mimic biosignatures. Take K2-18b, a sub-Neptune where Webb detected dimethyl sulfide, a compound overwhelmingly produced by marine life on Earth. The discovery electrified scientists, but false alarms loom. Unknown geology or photochemistry could create it too. Future missions like the Habitable Worlds Observatory, launching next decade, will tackle these ambiguities. With a space telescope designed to directly image Earth-like planets, it'll dissect atmospheric spectra with unprecedented precision, scanning for ozone, methane disequilibrium, and even surface features like continents. Every spectrum is a conversation. When Webb analyzed the 7 rocky worlds of TRAPPIST-1, it found thin or absent atmospheres battered by stellar flares, dashing hopes for complex life, but revealing resilience limits for atmospheres under red dwarf bombardments. Yet, the discovery pipeline accelerates. ESA's upcoming Ariel mission will survey 1,000 exoplanet atmospheres by 2030, cataloging chemical diversity like a cosmic taxonomist. Citizen scientists, too, join the hunt through projects like Planet Hunter's TESS, sifting through data for undiscovered worlds. As we decode these alien skies, we're not just filling databases, we're redefining what it means to be a planet, and perhaps what it means to be alive. But the journey is far from over. Peering into the chemical whispers of distant atmospheres was our first step onto the shores of a vast cosmic ocean. Now we prepare to sail deeper,
equipped with tools designed not just to glimpse alien skies, but to map entire worlds and listen for the faintest echoes of life. The next decade promises telescopes of unprecedented power, fundamentally shifting our perspective from statistical probability to intimate characterization. Imagine this. Missions like NASA's planned Habitable Worlds Observatory, HWO, ESA's Ariel, and concepts like LUVOIR or HABEX will be game changers. HWO, specifically designed for direct imaging, aims to block out the blinding glare of parent stars with starlight suppression technologies far beyond anything we have now. Think coronagraphs operating at levels of perfection measured in parts per billion, or perhaps even giant star shades flying tens of thousands of kilometers ahead of the telescope. This will allow us, for the very first time, to directly capture photons reflected off Earth-sized planets orbiting sun-like stars within their habitable zones. We won't just see a dot. We'll collect enough light to split into exquisitely detailed spectra, revealing not just atmospheric gases, but potentially their vertical structure, cloud cover patterns, seasonal variations, and even the presence of surface biosignatures like the red edge, indicative of widespread vegetation through its distinctive chlorophyll reflectance spike. The quest for biosignatures, however, is fundamentally an exercise in context and complexity. Detecting a promising molecule like oxygen or methane is thrilling, but it's only the opening note in a symphony that demands the entire orchestra. HWO and its kin will look for of gases in chemical disequilibrium, combinations unlikely to coexist for long without constant replenishment. Oxygen-methane is classic, but also consider nitrous oxide in significant quantities, or the telltale spectral signature of a surface ocean reflecting blue-green light under a haze layer. Crucially, we need to understand the planetary environment generating these signatures. Is the oxygen on a water-rich world or a desiccated desert where photochemical processes mimic biology? Is the planet tidally locked, subject to intense flares, or geologically active? Missions will increasingly combine atmospheric spectroscopy with measurements of the planet's orbit, its star's activity cycles, and even attempts to constrain its mass and density to infer a rocky composition. We are building multi-wavelength, multi-technique profiles of these distant Earths, synthesizing data into holistic portraits. And beyond biosignatures, we might even stumble upon artificial signals like narrowband radio transmissions or the spectral fingerprint of industrial pollutants like CFCs, a potential signpost not just of life, but of technological intelligence, expanding our search parameters into realms once purely science fiction. The acceleration of discovery isn't just about bigger telescopes, it's also about smarter analysis. The sheer volume of data from observatories like JWST, Plato, ESA's upcoming planet hunting mission focusing on bright stars, and eventually HWO will be immense. Artificial intelligence and machine learning are becoming indispensable tools. Algorithms trained on simulated planetary atmospheres and complex stellar variability patterns will sift through petabytes of light curves and spectra, identifying subtle signals of transiting planets or faint atmospheric features that might elude human eyes. Citizen science initiatives will continue to play a vital role, harnessing the pattern recognition power of thousands of volunteers in projects analyzing test data or classifying light curves from ground-based surveys. This democratization of discovery amplifies our reach. Furthermore, the potential for serendipity is enormous. Just as pulsars were discovered accidentally, our increasingly sensitive instruments scanning vast swaths of the galaxy could reveal phenomena we haven't even imagined. Exotic planetary types, bizarre atmospheric chemistries under conditions impossible in our solar system, or perhaps evidence of planetary system engineering on scales that defy comprehension. Every new instrument pushes the boundary of the possible, turning the unknown into the observable. Ultimately, the search for exoplanets transcends astronomy. It's a profound philosophical quest. Each newly characterized world, especially those hinting at potential habitability, forces us to confront fundamental questions about our place in the cosmos. Are we alone? Is life a cosmic imperative arising wherever conditions allow, or a fragile, improbable accident? Discovering even simple microbial biosignatures on a distant world would revolutionize biology, proving that the genesis of life is not unique to Earth and opening an entirely new field, comparative planetology of inhabited worlds. It would suggest the universe is teeming with biology. Conversely, if decades of searching with increasingly capable instruments find only sterile landscapes or ambiguous signals, it might imply that complex life, or even life itself, is extraordinarily rare. This search also pushes our understanding of planetary science to its limits. Systems like TRAPPIST-1, with its tightly packed rocky worlds, or scorched remnants orbiting white dwarfs, challenge every model of planet formation and evolution. They are cosmic laboratories where extreme physics plays out, teaching us about the resilience and diversity of planetary bodies under conditions we cannot replicate on Earth. As we stand on the brink of directly imaging Earth analogs and probing their atmospheres, we are not merely extending our catalogs. We are seeking to understand the cosmic context for life, rewriting the narrative of planetary evolution, and perhaps, just perhaps, preparing for the moment humanity discovers it is not alone in the universe. The starlight we capture carries not just photons, but the potential to redefine existence itself.